Welcome to one of the most intriguing puzzles in modern physics, negative capacitance in ferroelectric materials. Ferroelectric materials can exhibit negative capacitance, a phenomenon that challenges our basic understanding of energy storage in capacitors. Before diving into the puzzle, let's review what normal capacitance means. Capacitance is the ability of a system to store electric charge when a voltage is applied. The basic definition is C equals Q over V, where C is capacitance, Q is charge, and V is voltage. In a normal capacitor, positive charges accumulate on one plate and negative charges on the other when voltage is applied. For a parallel plate capacitor, C equals epsilon naught times epsilon R times A over D, where epsilon naught is permittivity of free space, epsilon R is relative permittivity, A is area, and D is separation. In all normal materials, capacitance is always positive. More voltage means more charge stored. For example, a 1 microfarad capacitor charged to 5 volts stores 5 microcoulombs of charge. Thus Q equals C times V equals 10 to the minus 6 times 5 equals 5 times 10 to the minus 6 coulombs. Now let's understand what makes ferroelectric materials special. Ferroelectric materials possess a spontaneous electric polarization that can be reversed by an external electric field. The atoms in ferroelectric materials form electric dipoles that all point in the same direction, creating a net polarization. Polarization P equals Chi times epsilon naught times E, where Chi is the electric susceptibility and E is the electric field. Common ferroelectric materials include barium titanate and lead zirconate titanate, also known as PZT. A key property is the hysteresis loop in polarization versus electric field, showing memory effects. This graph shows the characteristic S-shaped hysteresis loop of a ferroelectric material, where polarization depends on the history of the applied field. To understand negative capacitance, we need the Landau-Devonshire free energy theory. The free energy function describes the thermodynamic state of a ferroelectric material as a function of polarization. The Landau free energy is U equals alpha p squared plus beta p to the fourth plus gamma p to the sixth minus EP. Alpha, beta, and gamma are material-dependent Landau coefficients that determine the shape of the energy landscape. This creates a double-well energy landscape with two stable polarization states, shown by the red dots at the energy minima. The electric field is the derivative of energy with respect to polarization. E equals 2 alpha p plus 4 beta p cubed plus 6 gamma p to the fifth. Here's an important question. What happens to the material's response near the unstable central point of this energy landscape? Now we're ready to see how negative capacitance emerges. The differential capacitance relates how charge changes with voltage in the material. Differential capacitance C equals dQ over dV, which for ferroelectrics equals dP over dE. The inverse capacitance is dE over dP equals 2 alpha plus 12 beta p squared plus 30 gamma p to the fourth. Here's the critical insight. Alpha can be negative below the Curie temperature in ferroelectric materials. This graph shows that dE over dP becomes negative in a certain region, highlighted in yellow, meaning capacitance is negative there. When the slope dE over dP is negative, the capacitance itself becomes negative, violating our normal intuition. Let's understand what negative capacitance means physically using the S-curve. If we plot electric field E versus polarization P for a ferroelectric, we get a characteristic S-shaped curve. The middle section of the S-curve, highlighted in pink, has a negative slope corresponding to negative capacitance. A negative slope means that increasing polarization actually decreases the electric field, which seems counterintuitive. This negative capacitance region is thermodynamically unstable and normally cannot be accessed in bulk materials. The key question becomes, can we somehow stabilize this negative capacitance region to use it practically? The answer is yes, we can stabilize it by using ultra-thin ferroelectric layers in series with a normal capacitor. Let's see how connecting a normal capacitor in series can stabilize negative capacitance. We connect a ferroelectric layer with negative capacitance in series with a normal positive capacitance dielectric. This diagram shows the series connection of a ferroelectric capacitor with negative capacitance and a normal dielectric capacitor with positive capacitance. For capacitors in series, 1 over C total equals 1 over C ferroelectric plus 1 over C dielectric. If the ferroelectric capacitance is negative and its magnitude is larger than the dielectric capacitance, then the total capacitance can actually exceed the dielectric capacitance alone. Let's do an example calculation to see the stabilization condition. Suppose the ferroelectric has negative 10 picofarads and the dielectric has positive 8 picofarads. Then 1 over C total equals 1 over negative 10 plus 1 over 8, which equals 1 over 40. So the total capacitance is 40 picofarads, which is much larger than either component alone. This demonstrates capacitance amplification through the negative capacitance effect. Now let's understand why this only works with ultra-thin nanolayers. In bulk ferroelectrics, the negative capacitance state is unstable and the material spontaneously forms domains. In bulk materials, different regions form domains with opposite polarizations to minimize energy, preventing negative capacitance. When the ferroelectric layer is extremely thin, typically under 10 nanometers, domain formation is suppressed. The ferroelectric thickness must be less than about 10 nanometers for this effect to work. The series capacitor creates a depolarization field that provides a restoring force, stabilizing the negative capacitance state. This shows the key geometry: an ultra-thin ferroelectric layer of less than 10 nanometers on top of a thicker, normal dielectric. Let's address the apparent paradox about energy storage. An important question: does negative capacitance mean the system stores negative energy? The answer is no. The total system energy remains positive because we must consider the entire series combination. The total energy is 1/2 C total V squared, and C total for the series combination is positive. This energy versus voltage plot shows the total energy is always positive and increases with voltage, maintaining stability. The ferroelectric layer stores less energy due to its negative capacitance, but the dielectric layer more than compensates. The net effect is voltage amplification across the ferroelectric, which is useful for low-power electronics. Let's examine the experimental evidence for negative capacitance. Negative capacitance was first experimentally observed in hafnium zirconium oxide films around 2008. A typical experimental structure consists of a 3 nanometer HzO ferroelectric layer on top of an oxide dielectric on silicon. Key measurements involve capacitance versus voltage curves that show capacitance enhancement. Experiments show measured capacitance can be twice the value without the ferroelectric layer, demonstrating the amplification effect. These results have been confirmed by multiple independent research groups around the world. The most exciting application is in creating transistors with ultra-steep switching. Normal transistors have a fundamental thermodynamic limit of 60 millivolts per decade at room temperature. The subthreshold swing, SS, equals dVg over d log base 10 of ID and must be at least 60 millivolts per decade. Negative capacitance ferroelectrics can break through this Boltzmann-Tierney limit. This graph compares a steep slope transistor using negative capacitance in blue with a normal transistor in pink, showing much faster switching. This enables operation at lower voltages and dramatically reduced power consumption in electronic devices. This technology has tremendous potential for next-generation computer chips that are faster and more energy efficient. Let's work through a complete numerical example of designing a negative capacitance device. Our design goal is a transistor with a subthreshold swing of only 30 millivolts per decade. This requires the total capacitance to be twice the oxide capacitance. Let's say we have an oxide thickness of 2 nanometers with relative permittivity of 20. The oxide capacitance per unit area is epsilon naught times epsilon r times A over T. This gives us 88.5 microfarads per square centimeter. To get total capacitance of twice the oxide value, we need the ferroelectric capacitance to equal negative oxide capacitance. So we need C ferroelectric equals negative 88.5 microfarads per square centimeter. This requirement determines that we need an HfO thickness of approximately 3 nanometers. Such a device could operate at 0.5 volts instead of 1 volt, cutting power by 75%. Despite progress, several open questions and controversies remain. There is ongoing debate about whether negative capacitance is truly stabilized or just a transient switching effect. Some researchers argue it is a dynamic phenomenon occurring during switching rather than a static equilibrium state. The field is split between those who believe in static negative capacitance and those who see it as purely dynamic. A major challenge is that creating reliable and reproducible devices remains difficult due to material quality issues. We need better fundamental understanding of how ferroelectric materials behave at the nanoscale. Let's consider the broader implications of this phenomenon. Negative capacitance fundamentally challenges our textbook understanding of what capacitance means. It demonstrates the importance of thermodynamic metastability and how we can engineer and exploit unstable states. This shows the potential to create novel devices exploiting metastable states.